What if computers weren't just electronic devices? What if they were more like our brains? Our brains are incredible computational machines. They are able to process huge amounts of information at incredible speed with incredible efficiency. What if we took our current limited understanding of the human brain and built computers inspired by it? That's the vision behind neuromorphic computing. It's a field that aims to revolutionize how machines process information, making them faster, smarter, and more efficient. Salam everyone, this is Yusuf Saibati, and this is the first video of a series of videos where we are exploring neuromorphic computing by explaining what I learned and building some projects along the way. To be honest, I'm really excited for this series. I've been building in AI, XR, and brain-computer interfaces and have researched computational neuroscience over the summer and have really enjoyed the process. And now, I really want to explore the intersection between computation, everything that powers the AI, the extended reality, with the human brain. This time, we'll explore what is neuromorphic generally and why should we care about it. Neuromorphic computing is all about creating computational systems that mimic the structure and function of the brain. Traditional computers usually process data sequentially, like following some orders. However, our brains work differently. Our brains process data in parallel, while constantly adapting and learning from the world around it. Now, you might be asking, parallel processing? Isn't that what GPUs are great at? Well, yes, but there's a huge difference. GPUs are incredible at processing repetitive tasks in parallel, like training a deep learning model or processing graphics information from a game. However, GPUs are designed using traditional normal architectures, where they continuously process data whether it was relevant or not. This makes GPUs really powerful, but also power-hungry. Neuromorphic systems are different. Neuromorphic systems are directly inspired from the human brain, where our neurons, the basic architectures of our brains, communicate through electric spikes. Those spikes only occur in the brain when there is meaningful information to process. And this makes neuromorphic systems event-driven. Instead of running constantly, they only react when needed. Think of it like this. GPUs are incredible race cars on a fixed racetrack, where they constantly move at top speeds. However, think of neuromorphic computing as birds. They are agile, adaptive, and conserve energy by only flapping their wings when it's needed. This makes neuromorphic computing systems far more efficient, making them ideal for decisions requiring real-time decision-making. And that's a great segue to know why should we even care about neuromorphic computing? Well, there are three main reasons. First, energy efficiency. Our brains consume energy less than or similar to a small light bulb of 20 watts. And that is one of the goals of neuromorphic computing, which is achieving incredible energy efficiency levels. Second is real-time decision-making. Neuromorphic computing systems only process data when it matters, just like our brains. This makes it ideal for tasks like self-driving or robots, which require quick, real-time decision-making processes. Third, human-like thinking. Unlike traditional AI systems that are trained on predefined rules or data, neuromorphic computing systems aim to mimic humans, where they would be able to think, learn, and adapt just like us. Throughout this video, I might have oversimplified certain aspects or explanations, for example, whenever I talked about the GPU architecture or the brain's power consumption. In the upcoming videos, we'll delve deeper into those analogies and also understand the concepts behind them as we explore neuromorphic computing. In short, neuromorphic computing is all about smart, more efficient machines that will help us keep up with the demands of the future technologies. Now that we learned about neuromorphic computing and why should we care about it, how can we actually build with it? What's the hardware? What's the software? Let's start with the hardware. Neuromorphic computing relies on specialized chips that are built to mimic the function and structure of the brain. Even though they are built out of silicon, their architecture is completely different compared to normal CPUs and GPUs. Neuromorphic chips like Intel's Low-I or IBM's True North mimic how neurons and synapses work through electric circuits. These circuits communicate through short electrical pulses called spikes, just like neurons in the brain. Their architecture is what enables them to activate only when there is meaningful information to process. This event-driven system enables them to achieve the advantages we've mentioned before. Now for the software, which is equally important. At the heart of neuromorphic computing systems are spiking neural networks, or SNNs. They mimic how the brain works by processing data as spikes, or bursts of activity, rather than continuous data. This allows them to process information dynamically and adaptively, making them ideal for tasks like pattern recognition, robotics, and even brain-machine interfaces. To make SNNs work, neuromorphic systems rely on algorithms inspired by the brain, like the spike time-dependent plasticity, or STDP. These learning rules allow artificial neurons to strengthen or weaken their connections based on the timings of spikes, similar to how our brains learn and adapt from experience. This is the first video in a series about neuromorphic computing. The goal is to make this series weekly, posting by the end of 2025 about 52 videos. We'll make up for the missed videos. The goal of this series is to learn about neuromorphic computing and build up a couple of projects along the way, while developing my understanding of AI, enriching my understanding of neuroscience, and using both of those understandings to create real-world solutions. Along this journey, I'll be using tools like Nenjo, VBrain 2, or PySNNs to learn and develop projects in this really exciting area. And of course, I'll be posting tutorials, documents that I used throughout my research, and additionally in-depth articles about technical details or theoretical knowledge in the area. From the little time I've spent learning about neuromorphic computing, I'm really excited to learn more about its potential, especially in areas like healthcare and AI. And I'm really excited to talk to more people about this, especially experts or researchers in the space. If you would like to talk about neuromorphic computing, ask any questions or suggest anything for the series, please let me know. Salam. See you soon.